So as we move into the next lesson, this is going to move into um, some basic operations with square root radicals. So remember, in math, we have these inverse operations. So if you recall, like if I have, say, 8 plus 2, we would say that's 10. Inversely, which means kind of go backwards, I can create a subtraction statement. So I could say 10 take away 2 is equal to 8. Similarly, if I give you a subtraction problem, say, 22 take away 2 is 20, you can go inversely the other direction, and the subtraction problem turns back into an addition problem. So inversely, we would say 20 plus 2 will get me back to 22. So I have this inverse thinking going on. Similarly with multiplication and division. So if I have like 3 times 5, we'd say, try it again, 3 times 5. So we'd say 3 times 5 would be like 15. Inversely, we'd go backwards and say, we'd say 15 divided by 5 would get me back to the 3. And that would be a true statement as well. Or if we had a division problem, say 10 divided by 2 would equal 5. Inversely, we could say 5 times 2 gets me back to 10. So each operation in math has an inverse operation. So those are our 4 basic operations: adding, subtracting, multiplying, dividing. But there are some other operations out there. Another operation we have is what's called squaring. So like if I have 5 squared would be 25. And if we go backwards inversely, there's an operation that is inverse of squaring. And this is described as the square root button. So we would take the square root of 25, and that would get us back to 5. So that's where these radicals come in, is they're the inverse of powers, if you will. So this little symbol here, this looks like a division symbol, but it's not. This is actually the radical symbol. So the radical symbol is involved in working with roots. The roots we're dealing with mainly are what we call square roots. Back in the day, there used to be like a little index number of a 2 here, but the 2 is no longer placed there. So now if we see just the radical symbol by itself, it's understood to be the square root symbol. So this symbol is described as the square root symbol as well. So it's the inverse symbol of squaring. So with radicals, like we said, if I give you the square root of 36 is equal to something, what we do is we do inverse thinking, and we ask ourselves, well, what squared actually gives me 36? So if I can answer that question, I've answered the square root problem. And notice that we do know that 6 squared does give me 36. So the square root of 36 is that 6. It's what squared that gave me that. So one way to do square roots is just understanding what squared gives me that. So if you understand that, 2 squared is equal to 4, then you should understand that the square root of 4 is going to get me to 2. 3 squared is equal to 9. So the square root of 9 is going to get me back to the 3. 4 squared is equal to 16. So the square root of 16 takes me back to the 4. 5 squared would be 25. So the square root of 25 is going to take me back to the 5. 6 squared would be 36. And if I go backwards, the square root of 36 is going to take me back to the 6. And I could keep doing that for all numbers. So if you square a number, then you can go backwards and take the square root of that number. Now, in this section here, we're going to do something a little bit different. So another way of looking at this is to rewrite 36 as a factor pair. So since there is a pair of 6s, what we can do is 1 6 can come out of the radical symbol as a way to do the problem. So if I look at this problem as, square root of 36, another way to look at it is I can write this as a factor pair, 6 times 6. And what we pick up on is with radicals, for every pair of 6s that are inside there, 1 is going to come out. So 1 6 would come out as that. So what we pick up on is one factor comes out for each pair of factors that we have. So it's kind of a 1 for 2 concept. So if I have the square root of 16, notice that I can write a factor pair for 16. We know that 4 times 4 is 16. Since there's a pair of 4s, that means we have a perfect square present. And what that means is 1 4 can come out of the radical. So this turns into just simply 4. So for every pair of the same factor, one of those factors can come out of the radical. Now, sometimes the number doesn't have a factor pair. In this case, the radical remains in the problem. This number is described as irrational, which is going to be some type of non-repeating, non-terminating decimal. Most often, we just leave this as a radical. So for instance, if I give you the square root of 6, what squared is going to give me 6? Well, we know that 2 squared would be 4, and 3 squared would be 9. So we know that the square root of 4 would be 2, and the square root of 4 would be 2. Let's try that again. It's all a little too messy. So 3 squared was 9. Again, if I take the square root of 4, that would be 2. The square root of 9 would have to be 3. So notice how the square root of 6 is going to be somewhere between the square root of 4 and the square root of 9, which means we have to be somewhere between 2 and 3. Well, that's the world of decimals. So one way to kind of play with this is using a calculator. I could kind of guess and check and say, well, let's choose 2.5. If I square 2.5, does it give me 6? Well, that gave me 6.25. That means it's a little bit too high. So if I want, I could do 2.4 and square that, and that would give me 5.76. That's too small. So the square root of 6 has to be somewhere between 2.5 and 2.4. So if I do 2.45, try it again, 2.45. If I square that, that gives me 6.0025. That's pretty darn close. But let's try 2.44. Get that. Oop, got to square it. Try that again. 2.44 squared. And that gives me 5.9536. So that's a little bit off. So the answer's got to be between 2.45 and 2.44. So if I try something like 2.445, hit enter, notice that I have to square that, 2.445 squared, hit enter. Notice that that's too small. So I'd have to pick something higher than 2.445. So I can maybe try it like 2.446 squared. And that would be closer, but I could still go a little bit higher. So then I can go like 2.447 squared. And I'm getting a little bit closer. So I could do like 2.448 squared. And I'm still go a little bit higher. So 2.449 squared. And notice that I can still keep going. So notice how we keep playing with that. So we can kind of go back and forth. So what we pick up on as we do this is I could keep doing this forever until I got a really good answer. But most of the time in like books, we would usually just do 4 decimal places. So I'd be getting really, really close at this point. Now, the quick thing on a calculator is we actually have a square root button on the calculator. So we can actually do this. Shorthand would be use the square root button on the calculator and put that in and hit enter. Notice that it does give us this 2.44948. So notice how I was getting pretty close there. I had 2.449 and I was getting right on top of it. So if I kept going, I would have like 2.4495. That would be a really good estimate of the square root of 6. So but notice how the answer here on the calculator is it's a non-repeating decimal. So notice how there's no decimal that's repeating. And this decimal actually is not terminating. It just keeps on going. But on this calculator, it actually has to shut it down. So the square root of 6 is actually considered an irrational number. So he's part of a different number system than that we're used to. So if we have the square root of 6, instead of changing it to a decimal, most often we just leave this as the square root of 6. So the next thing we'll get into is adding and subtracting radicals. So a radical can be added to what we call a like radical. Like radicals have the same value inside the radical. To add like radicals, all we do is add the coefficients of each and keep the radical and the number inside. So if you recall, like if I'm adding like terms, if you remember in algebra, like if I gave you, 2x plus 3x, we call those like terms. When you had like terms, you just added the coefficients and you would say that answer is 5x. So adding like radicals is very similar. Notice how we have the same radical. We have the same square root symbol and the same number inside of it. So since they have the same square root symbol and 5 inside there, we call these like radicals. So all we have to do is add the coefficients in front and say, 2 plus 4 is going to be 6. So therefore, this would be 6 times the square root of 5 would be the answer. So all we do is add the numbers in front and keep the radical part the same. So let's have 9 squared root 3, take away 9 squared root 3. We would consider these like radicals. So all I have to do is subtract the 7 minus the 9. So that would be a -2. So that would be -2 square root 3. So yes, we can have negative numbers here too, negative decimals, or in this case, negative irrational numbers, since that doesn't actually simplify. So 5 radical 11 minus 5 radical 11, well, 5 minus 5 would be 0. So in other words, there's not anything left. So those we call those opposites, they would just cancel out and get 0. So if I have 2 square root 2, take away the square root 2. Remember, there's like a coefficient of 1 here that we have. So if I have 2 square root 2's, take away square root 2, that's going to leave me with 1 square root 2, or we just write square root 2. So if we look at this example here, we have 3 square root 5 plus 5. Notice this 5 is not inside a square root symbol. So these are considered unlike radicals or unlike terms. So this is actually simplified as is. We cannot actually add those together. So that has to remain as is. Similarly, the square root of 7 minus 7, notice how the 7 is not inside a radical. So these are considered unlike terms. So this is also considered simplified. So we don't go any further with that, unless I use the calculator to change it to a decimal. And we're not going to do that at this time. So another thing we may have to do is what we call simplifying radicals. So to simplify radicals, what that means is search out perfect squares inside the radical. So the way we do this is we're going to rewrite the number inside as a prime factorization, and we're going to seek out what we call factor pairs. These factor pairs are going to represent perfect squares. So again, it's kind of a 1 for 2 thing. So one factor comes out for each pair, and then the leftovers stay inside the radical, and then we're going to multiply if necessary. So one way to simplify the square root of 12, because again, nothing squared gives me 12, is what I can do is do a prime factorization on 12. So what I do, I like to use what we call the big T, the T-chart. And remember, my prime numbers are this 2, 3, 5, 7, and 11. And sometimes we do use 13. So most often I rarely get past 2 or 3, maybe even 5, but we'll see where this goes. So I start with 2 and ask myself, is 2 a factor of 12? Well, 2 does go into 12 6 times, so I'll go ahead and do that division. I'll write the answer, the other factor on the other side. So now we have to break down the 6 into a prime number. So the 2 does go into 6 3 times. Notice 2 no longer works for the 3, but 3 is a prime number, and 3 does go into 3 1 time. So once I get that 1 there, we've completed our prime factorization. So what we do is we rewrite the square root of 12 as 2 times 2 times 3. And what we're looking for is we're looking for a factor pair. But notice how there's a pair of 2's here. So since there's a pair of 2's, what we're allowed to do is bring 1 2 outside. And since there's not a pair of 3's, that 3 remains inside the radical. And so this is our answer, 2 times the square root of 3. And this is considered simplified. That's what we mean by that. So if we have a perfect square inside there, we want to pull it out. Notice that 2 times 2 would have been the same thing as 4. And we could have took the square root of 4 and got 2. But this is another way to look at it. So to simplify the square root of 50, again, I can use a prime factorization because nothing squared gives me 50. So we know 7 squared is 49. That's too small. 8 squared is 64. So it's not a perfect square. So we're going to see if there's any numbers that are perfect squares that are factors of 50. And we're just going to use the prime factorization to do that. So again, we do know that 2 goes into 50 25 times. 2 doesn't go into 25, and neither does 3. But 5 does. 5 goes into 25 5 times. And we do know that 5 goes into 5 1 time. So again, this left side becomes our prime factorization. So this turns into 2 times 5 times 5. So now what we're looking for is that pair. And notice how we do have a pair of 5s here. So that pair of 5s, this is a 1 for 2 concept. So we're going to bring out 1 5, and then we're left with this 2 inside there since it's not a factor pair. For every 2 5s, we bring out 1 5. So the 5 comes out, so there's no more 5s left inside there, and then the 2 is left over. So that's considered simplified. So if I look at this problem right here, we want to add these 2 radicals. But before I'm going to add these 2 radicals, we also have to make sure they're simplified. Well, 5 can't break down any, so there's no way there's going to be a factor pair for 5. But 20 has plenty of room to break down. So what we want to do is break down the 20 and see what we come up with. So 2 does go into 20 10 times. 2 does go into 10 5 times. 2 does not go into 5. 3 doesn't go into 5. But 5 does go into 5 1 time. So what I can do is I can rewrite the square root of 20 as 2 times 2 times 5. So I'm going to go ahead and bring everything else down with it. So I'm going to bring down the 12 square root of 5 plus the 3 times the square root of 2 times 2 times 5. Notice how we do have a pair of 2's. So that means that 1 2 can come out. So this leaves me then with this 12 square root of 5. And then as I was saying, this turns into 3 times 2. And then the 5 stays inside there. The 3 times 2 can now be multiplied together. That's going to give me 6 square root of 5. And then we also have this 12 square root of 5. So now we're at this spot. So now each one of those is simplified. But notice now they are actually like radicals. So I would add the coefficients together and say this is 18 square root of 5. And that would now be completely simplified. So if I want to simplify the square root of 3 minus the square root of 27, right now they're not like radicals. But the 27 looks like it can be simplified a little bit further. So if I bring the 27 over here and do a prime factorization, again, my prime numbers are 2, 3, 5, 7, 11, and sometimes we use that 13. So again, I'm looking at that. 2 does not seem to work, but 3 does go to 27 9 times. Again, if you need to use a calculator for that, you can. 27 divided by 3 on a calculator would give us 9. And then 3 would go into 9 3 times, and 3 would go into 3 1 time. So 27 is really just 3 times 3 times 3. So I can rewrite that as then 3 times 3 times 3. So I'm going to bring down the rest of the problem. So square root of 3 and a subtraction. But notice how, again, we do have a factor pair of 3's here that we can kind of pull out here. So a pair of 3's is going to come out as a 3. So this is going to become then 3, and 1 3 is going to be left inside there. And then the square root of 3 is going to come down, and the subtraction sign is going to come down. So remember, this is just 1 square root of 3. So since we do have like radicals, we can subtract. 1 take away 3 is going to give us this -2. So -2 square root of 3 would be the answer to this problem. So that would be simplified. So sometimes when you add or subtract, you actually have to simplify before we combine the 2 radicals together. The next thing we want to get into is we want to multiply, or we're going to divide square root radicals. So another piece of vocabulary we need to pick up on is the number inside the radical is called the radicand. So notice how we have over here 5 times the square root of 7. The 5 is described as a coefficient. The number inside the radical is called the radicand. So we have a new vocabulary word that we want to kind of pick up on. So when multiplying square root radicals, what we do is we multiply the coefficients together and we multiply the radicands together, and then we simplify if possible. So the way we can do this is we can multiply the 2 times 3 together, and we can multiply the radicands together. So it's going to be like 5 times 4, and we leave them both in the radical. So 2 times 3 is going to be 6. 5 times 4 is going to be 20. Now, before I stop, I got to make sure the square root of 20 is simplified. And I think we recalled earlier that can actually be broken down. So again, using my prime numbers, 2 would go into 20 10 times, 2 would go into 10 5 times, and 5 would go into 5 1 time. So the square root of 20 does break down. So it's going to be 6 times then 2 times 2 times 5. So from there, we're looking for a factor pair. And notice how we do have a factor pair of 2's. So that means we can bring out 1, 2, and that 2 is going to be multiplied to the 6, which makes that become a 12. And we have 12, and then the 5's left over. It stays inside. So 12 square root of 5 would be the simplified answer of multiplying those two radicals together. So if I look at this example here, 9 times x squared y, this isn't really multiplying, but we do need to try to simplify this a little bit. So to simplify this, note that the 9 is a perfect square. And if you don't see it, though, we can do our factor pairs. 3 does go into 9 3 times, and 3 does go into 3 1 time. So the way to do this problem, if you want, is kind of break it all back out, expand it. So the 9 would be 3 times 3. The x is really 2 x's, and then there's this y here. So we're looking for these pairs. So notice how there's a pair of 3's and there's a pair of x's. So that means we can bring out 1 3 and 1 x, and that leaves me a y inside the radical. So we'd rewrite that as 3 times x times the square root of y. That would be the simplified version of that. So if we have the square root of 3 times the square root of 12, what we want to do is multiply the radicands together. So this turns into the square root of 3 times 12. So this turns into 3 times 12 would be 36. We actually know what the square root of 36 is. The square root of 36 is actually 6. So we would be kind of done with that problem. So the square root of 2 times the square root of 6, notice how, again, we would multiply the two radicands together. So that would be the square root of 2 times 6. So it's going to turn into the square root of 12. Now, the 12 would have to be broken down because I'm not sure what squared gives me 12. So I'll put the 12 up here and use my prime factorization. So 2 does go into 12 6 times, 2 does go into 6 3 times, and 3 does go into 3 1 time. So that means I can rewrite the 12 as 2 times 2 times 3. So again, we're looking for that factor pair. Notice how there's a pair of 2's. So that means 1 2 is going to come out. We have 2 times the square root of 3. Okay. So on this one, we have multiplying and subtraction going on. So we're supposed to be following the order of operations. But if you look inside the parentheses, the square root of 7 minus 2, those are not like terms. So I can't actually do what's inside the parentheses. So we have this distributive property that we used earlier in Unit 1. So remember, the distributive property means to multiply the outside number through the subtraction, or we would also call it addition, since this is really a square root of 7 and a negative 2. So we really would multiply the outside number to both inside numbers. Now, when you multiply 5 times the square root of 7, the 5 is like a coefficient, the 7 is like a radicand, so they don't actually go together. So it's just going to stay 5 times the square root of 7. The 5 remains as a coefficient. The 7 remains as a radicand. But notice how we have 5 times 2. Those can be multiplied together, and that would give us a 10. The square root of 7 cannot be simplified in these, so that would be as far as this goes. This would be considered simplified since those are not like radicals. Another thing we have is we have 2 plus the square root of 3 times 5 plus 2 square root of 3. This is a little bit different than we've done. So if you recall back in the day when you were learning multiplication, well, if I gave you 15 times 12, to do this multiplication, we learned that you go 2 times 5 is 10, carry a 1. 2 times 1 is 2, plus 1 is 3. That's 30. We put a 0 down. We go 1 times 5 is 5, and 1 times 1 is 1, and that would be 180. So the question is, how would that help me multiply these two terms together? Well, it don't. But this is considered a shortcut before the calculator. You can also use what's called the area model. If I want to multiply 15 times 12 together, what we could do is create a little model here of a rectangle, and area means to multiply the edges together. But what's interesting is 15 can actually be broken apart as a 10 and a 5. A 12 can be broken apart in a 10 and a 2. So instead of trying to find one big area, what we can do is find 4 smaller areas. So if we do this math, what this means is the 10 would have to multiply to the 10, and the 10 would have to multiply to the 2. So that would give us 120. And then what would have to also happen is this 5 would have to also multiply to the 10, and this 5 would have to also multiply to the 2 to get each area of each one of these. So that's going to be 50 plus 10. So then if I add all that together, 100, 170, 180, that would be the answer. So notice that also gives us the answer. So it's like, why would we want that? Well, this is not bad. It's kind of closer to this. Another model we can use to get this multiplication problem done is I can write this as 10 plus 5 times 10 plus 2. So if I have 10 plus 5 times 10 plus 2, how the math works is this is like distributive property twice. I got to multiply the 10 to the 10 and the 10 to the 2. So this becomes 100 plus 20. And then you got to multiply the 5 through. So the 5's got to go to the 10 and the 5's go to the 2. So that's going to be plus 50 plus 10. If we add all that together, that would be 180. So what we're seeing is this math here looks more closely related to this type of math. So this doesn't really help us a whole lot here, but this does. So when I work this problem out, we're going to multiply the 2 through each piece, and then we're going to multiply the 3 through each piece. So in math, this is called FOIL, F-O-I-L. So when you multiply the 2 to the 5, those are considered the first terms. So 2 times 5 becomes my first move. Plus then the 2 times the, so we have this 2 over here times the 2 times the square root of 3. That becomes my outer terms, my second move. So we now have 2 times the 2 square root of 3. That's considered our outer terms. And then we move to the inside. The square root of 3 times 5 becomes our next move. So the square root of 3 times 5 becomes our next move. And then those are considered our inner terms. And then the square root of 3 is then multiplied by 2 times the square root of 3. That becomes what we call our last terms. So what we have are 4 little individual problems we have to work out. So 2 times 5 is going to be 10. That's not so hard. 2 times 2 times the square root of 3, that's going to be pretty easy. That's going to be 4 square root of 3. Square root of 3 times 5, we usually like to write the 5 as a coefficient. So that's going to be 5 times the square root of 3. That's about all we can do with that since the 5 is the coefficient and 3 is a radicand. Nothing to do there. Here, we can go 2 times the square root of 3 times the square root of 3. So if we rewrite that as 2 times the square root of 3, notice how we have 2 radicands there. So as I come across here, I see the 10. The 4 plus the 5 are like radicals. That's going to be a 9 square root of 3. Over here, though, notice how we have 2 3's inside there. That means 1 3 can come out. That means that's going to be 2 times 3. So notice how 2 times 3 is actually going to be a 6. So that's 6 plus then 9 square root of 3 plus 10. So that means the final answer is going to be 16 plus 9 square root of 3 would be our answer. So that's what we mean by using what's called FOIL to do the problem. So if I want to divide square root radicals, so this is where we're going to get into what we call fractions and reducing fractions. So to reduce fractions, what we have to pick up on is coefficients can only reduce coefficients. Radicands can only reduce radicands. So we want to simplify as possible. So notice how this 3 is a coefficient and the 6 is also the same way. It's not inside the radical. So these are friendly. But notice how this 6 here is inside the radical. So this 6 is a radicand. So this 6 inside the radical cannot go with the 6 that's outside the radical. So those are not like. But the 3 and 6 are. So what we could do is, if we want, we can use a prime factorization on the 6 on the bottom here. That's going to be 2 goes to 6 3 times, and then 3 would go into 3 one time. So what I pick up on is this is going to be 3 times then the square root of 6 over 2 times 3. What we pick up on is there's a like factor in the top and bottom, and with fraction math, you just divide those like numbers out. So I'm left with the square root of 6 over the 2. Notice how the 6 is inside the it's a radicand, and the 2 is not inside the radical, so it's not a radicand. So I cannot touch those. So we have to leave that alone, and that's considered a simplified at this point. So if I have this 5 square root of 20 over the square root of 10, notice how we have like 5, and notice how these are the same radical. So I could actually write this then as the square root of 20 over 10, since they're both in the radicand. And we didn't know what 20 divided by 10 is. So 10 goes into 20. That would actually be 2 times. So that's going to be 5 times the square root of 2. So that would be our answer to that problem, is just because we can actually divide 20 by 10 and do our division. So this problem right here looks like a crazy question. One way of doing this is just break everything down. So the 8, notice the 8 would be really a 2 times a 2 times a 2. X cubed would be x times x times x. 9 is the same thing as 3 times 3 times then x squared is x times x. So if I want to, I can do it from this direction. On the bottom, we have this 2 times x on the outside. Square root of 16, we may want to do a prime factorization on it. So we have 2 goes to 16, 8, 2 goes into 8, 4, 2 goes to 4 twice, and 2 goes into 2 one time. So what we have here is then the square root of 2 times 2 times 2 times 2 times then x times x times x. We can also simplify these radicals. So for 2 3s here, this means 1 3 can come out. And since there's 2 x's, that means 2 x's can come out. So on the top, what we have then is a 2 times a 2 times a 2 times a 3 times a 3 times then an x times an x times an x. And then, wait a minute, only 1 3 comes out. It's a 1 for 2 concept. Let's back that up. Try that again. So it's a 1 for 2. So only 1 3 comes out. We already have 3 x's out. And then 1 more x comes out. So that's what's in the numerator. On the denominator, notice how there are 2 pairs of 2's here. So if there's 2 pairs of 2's, I can bring out 2 2's. So this becomes then 2 is already out there, and 2 more 2's come out, times 2 times 2. And since there's also a pair of x's can also bring out 1 more x. So we already have 2 x's out here. 1 more x is going to join it. So that leaves me then with the square root of x in the bottom. So then we can just start whacking away and canceling things. So if I'm canceling, this 2 divides this 2, this 2 divides that 2 divides that 2, this 3 stays put. This x divides this x divides this x, this x divides this x. So everything is dividing out except for a few things. So what we're left with then on the top is a 3x. And what's left on the bottom is the square root of x. So this is going to bring us into something else, rationalizing the denominator. So many times the radical symbol is not left in the denominator. So the denominator is rationalized. So notice how this question up here, we actually need to go one more step. We don't like to have the radical in the denominator. So the way we solve this is we multiply the denominator by itself. But remember, if you multiply the denominator by something, you have to multiply the numerator by that same factor to keep the fraction equivalent. So notice how I have 5 over square root of 7. There's really nothing I can do because the 5 cannot touch the 7 inside the radical, and even if it could, it can't do anything. So what we do to simplify this is we multiply the denominator by itself by another square root of 7. But we also got to multiply the top by the square root of 7. So then we multiply straight across. 5 times the square root of 7 is still going to be the 5 times the square root of 7. But also on the bottom, since we have 2 7's inside the radical, 1 7 comes out, and that leaves me just a 7 on the denominator. Notice now we don't have any like fractions to deal with, so we leave that as our answer. That's now simplified. So if we have 2 over the square root of x, again, we don't want that square root of x on the bottom, so we can multiply the bottom by the square root of x as long as we multiply the top by square root of x. So this is going to give me 2 square root of x on the top. And then if there's 2 x's inside the radicand, that means 1 x can come out. So that becomes then 2 square root of x over x. So if I looked at our problem up here, we probably need to go one more step. I probably would need to multiply this by radical x and this by radical x. And then that in turn would have turned into 3x squared root of x over x. And then we actually could have marked out these 2 x's, and now we would have had 3 squared root of x as a final answer. So that's interesting. So lastly, we have the square root of 8 over the square root of 12. Again, it's not a bad idea to use a prime factorization. So remember, an 8 is a 4 and a 2, or 2 times 2 times 2. A 12 is like a 4 times a 3. In other words, 2 times 2 times 3. So since everything's inside the radicands, we can start canceling. So this 2 cancels with this 2. This 2 cancels with this 2. So now we're just left with the square root of 2 over the square root of 3. But notice how we still have a radical on the bottom. So we want to multiply the denominator by the square root of 3 as long as we multiply the top by the square root of 3. So since we have a radicand and a radicand, that's going to become a radical 6. And since we have 2 3's inside the radicand, inside the radical, that's a 1 for 2 concept. So we come out with a 3. But also we can't go any further than that. So that would be considered our simplified answer for that. All righty. So that takes us to a gambit of problems involving radicals. Hopefully you found that useful. Have a good day.